All right, let's continue our discussion of phases of matter and how they interact with heat. And that's going to bring us to something that we call phase diagrams, where we're looking at how the phase of matter changes with various pressures and temperatures. So in order to show how substances change in response to pressure changes or temperature changes, we use a thing called a phase diagram. And phase diagrams are fairly easy to understand. They're very graphical, and we can take a look at what our conditions are, what we want conditions to be, and we can see what phase of matter a substance will be in. So the graph is characterized by regions of the three main phases, and then we have boundary lines where the two phases are in equilibrium. And the really nice things with these phase diagrams is that we can see how those phase boundaries change as our conditions change. There is a point for pretty much every substance where all three phases exist simultaneously in equilibrium. So gas, liquid, solid are all in equilibrium with each other, and we call this the triple point. So here, if we look at the phase diagram for water, we see here we've got solid inside this area here. We've got an equilibrium line here between solid and liquid. And so if you move over here, we're now in the liquid area here. And then down in here, we are completely in gases. And so if we look at some things that we know about water, if we go at 0 degrees Celsius, at 1 atmospheric pressure, or roughly 1 bar of pressure, we are right here. And that puts us right on the line between solid and liquid. And we know that that's the melting point for water. And so we know that that is where water is in equilibrium with itself between the solid and the liquid phase. If we move to a slightly colder temperature, maybe here, which looks like, I don't know, maybe -10, and we come up to our pressure, we are solidly in the solid phase. So we know that for basically atmospheric pressure and we're at -10 Celsius outside, we're going to have ice on the roads or ice in the puddles. If we're above zero, so maybe it's 5 degrees Celsius outside and roughly 1 atmospheric pressure, we know that water is going to be in a liquid phase. Hopefully we never go walk outside and have it be 100 degrees Celsius. We do here have a triple point that we talked about, where you have your fusion curve, where you have solid and liquid in equilibrium with each other. You have the sublimation curve here, where solid and gas are in equilibrium with each other, and notice that the pressures are fairly low for that to exist. And then here you have your liquid gas curve, your vaporization curve, where the liquid and gas are in equilibrium with each other. But because of the shape of your fusion curve, it's pretty much always going to cross. I don't know of any substances where it doesn't cross, but that doesn't mean that there aren't any. But because of the shape for water, you do get a point where these lines all cross, and we call that a triple point. And so it happens just a little bit above freezing and down a little bit below atmospheric pressure. And so if we want to figure out how to navigate within a phase diagram, you just need to look at where you're at and where things are going. And so here we have 1 atmosphere of pressure, so that's our normal atmospheric pressure. And if you go across here, you see that we reach a temperature right around 0 Celsius for our freezing point, and that moves us into a liquid. And if we're at 25 Celsius, we're solidly within a liquid. And as we move up, we get to 100 degrees Celsius. And that's when we start to turn into a gas. So you just need to figure out what pressure you're at, what temperature you're at, and that can tell you where you need to be and what phase you're going to have. We mentioned the triple point here. And so it's at 0.01 Celsius temperature, so just a little bit above freezing, and at 0.006 atmosphere, so very low pressure. I don't know if that's actually true for water or not. Now, you may have heard of this process or not. This was a little bit bigger when I was a child. We used to hear about freeze drying for certain things. If you're used to like camping, you go camping a lot and you buy food, it might be freeze dried. So you hear this term freeze dried. And what this idea of freeze drying is to remove the water from a food without having to heat it up over the boiling point of water. And there's an easy way to do that using these phase diagrams. You can adjust the conditions and get water to evaporate out of the food without having to cook the food at high temperatures. So if we want to freeze dry something, what we can do is we can bring a sample of water or something that contains water to its triple point. And then if we maintain the pressure but warm it up just slightly, we will move that phase into the gas phase. And of course, once water gets into the gas phase, it's going to leave whatever sample it happens to be in and evaporate away as long as it's got somewhere to go. So what this does is it allows food to be frozen, thus preserving it, but then you can remove the water from it, and then that dries it out and allows you to reconstitute that food later by adding the water that had been removed. And what this does is it preserves flavor. It also preserves the food and allows it to be packaged for a considerably long time. And so we can go back and look at this idea here. So if we take a food and we bring it to its triple point right here, so we can see we're below our atmospheric pressure, but we're just a hair above the freezing point here, and so we've got all three phases of water in equilibrium with itself. Now, if we raise the temperature just a little bit, so maybe just to like 10 degrees Celsius, we get into this point. And if we go straight without changing the pressure, notice that the liquid equilibrium line goes up. And so if we go straight, we're going to end up right in the gas area. And so now all of your water that's there is going to be in a gas phase, and it's all going to evaporate. Now, if we look at something like carbon dioxide has a very interesting phase diagram. There's a lot of substances that have interesting phase diagrams, but CO2 is one of the more common substances, and you may be familiar with some of its interesting phases. Now, at normal pressures, so regular atmospheric pressures, the liquid phase doesn't exist at any temperature. You can't turn CO2 into a liquid at any temperature based on the phase diagram. And so if you have solid CO2, remember that's dry ice. If you've ever played with dry ice, you know it never liquefies. It just turns directly into a gas. It sublimes. As soon as it warms up at room temperature, it never melts. It just turns directly into a gas. Well, here's our phase diagram for carbon dioxide. Now, at 1 atmosphere, you have to get pretty cold. You've got to take it down to minus 78.5 degrees Celsius just to get it into a solid state. Any colder temperatures than that, and it's just a solid at a colder temperature. Any warmer than that, and it turns directly into a gas. Now, if you want to take it to its triple point, you have to take it all the way up to 5 atmospheres of pressure just to get liquid in equilibrium with any of that. If you want your carbon dioxide to be in a liquid state at all, you have to go higher than 5.1 atmospheres to get it into a liquid state, and something warmer than minus 56.7 at most pressures. But that's a pretty significant amount of pressure in order to liquefy CO2. It can be done with mechanical equipment, obviously, and we do use that quite a bit. CO2 makes for a very nice non-polar solvent. It's very good at dissolving things under high pressures. And then when you want it to go away, all you need to do is lower the pressure, and the CO2 evaporates back into a gas and can be dispersed, and you're left with your separated material.